and we can start the lecture. Okay, for this video. Okay, so the topic of today's lecture, today I'll try to cover two topics. One of them is starfish lemma, and another I would like to return to grass manuals, which we discussed in some particular case on the first lecture. Now we start discussing in more full generality, but probably will not finish today. But first, about starfish lemma. So what is the problem which we are trying to address? So let A be some cluster algebra. Let me recall that cluster algebra is the algebra generated by A variables. Generated by all A variables. By all, let me write it that A of T bar related to T prime related to our T by some sequence of notations. There is a similar notion of upper cluster algebra. So this is A bar is intersection of the rings of Laurent polynomials of A plus minus of T prime, all T prime related to T. So this is an algebra of functions, of rational functions, which are Laurent polynomial for each seed. One can also say that A bar is a regular function of A cluster variety, which was what definition is obtained by gluing all the tori, which correspond to A seeds. So this is just by definition. One can ask, so we define algebra, one can ask, can this algebra be defined with some known algebra, or some, better to say it, or some algebra which has some geometric mean? So we want to have A or upper cluster algebra, A bar. Quite often they are actually isomorphic, to be isomorphic to some algebra R, which is an algebra of function of some X, where X is affine, or actually not necessarily affine variety. So if you want to prove isomorphism, we first have to construct a map and then to prove that it is injective and surjective. Starfish lemma, which I'm going to talk about very soon, is a tool to prove one of the inclusions. So if we want to assume that we have a map from A to field of rational functions. So that original generators of the cluster algebra goes to the field of regular ring of regular functions. So we have a map. We want to prove that the image is isomorphic to C of X. So for this, we need to observe two statements. First statement that want that phi of a bar contains ring of rational functions. How to regular functions. So in order to prove it's sufficient to find some generators in and show that these generators belongs to image of the, say, upper cluster. But there is an opposite question: how to show that image of all upper cluster algebra is consists of regular functions, belongs to R. In principle, this is difficult. I mean, we have to prove that for any seed, image of all all variables belongs to regular function. For usually there are infinitely many seeds, so it requires infinitely many checks. But there is a quite standard theorem. There is a theorem which greatly simplifies such checks, and this is so-called starfish lemma. Okay, I prepared the figure of the starfish from the Wikipedia, but I don't know why it's called, what's fish about, but star is because the criterion given in terms of the star of the vertex. So we consider initial seed T, and all seeds are related to T by one mutation. The theorem is like this. So we are in the setting as above. R is a ring of regular function of some variety of here are conditions normal and irreducible. And let's assume that we have some seed T, which has a quiver, which I encode by is adjusted matrix P, and variables A. And assume that we have a map from the ring of rational functions, from the field of rational functions A to the field of rational function on the variety X. And map is such that all initial cluster algebras are regular functions. These regular functions are pairwise coprime. And also, if we perform one mutation in the letter I, then image of the corresponding cluster element AI prime also is also a regular function and coprime to the image of AI. Then starfish lemma says that the image of phi of the upper cluster algebra belongs to R. Some remarks are in order. First, I want to say that usually X is not smooth. It has singularity, but here it is assumed that X to be normal. I'm not going to recall what was the definition of the normal variety, but I give a criterion which is usually used in such setting. The criterion is that if ring of regular function X is factorial, or in other words, we have unique factorization domain. Then X is normal. In case of unique factorization domain, coprimeness means that if we have two regular functions, we take zeros of one function, zeros of another function, then a set of zeros, an intersection of this sets of zeros has codimension 2. No, this is general definition of the coprimeness here. But in case of unique factorization domain, we have quite natural notion of the prime elements, and there is no common prime divisors on both. If two elements are coprime, they have no common prime divisor. Okay, so let me write what I just said. So two elements, I don't know, F and G goes to R prime. Set F equals 0, G equals 0 has a dimension greater than or equal than 2. If our ring R is factorial, then coprime means that greatest common divisor on the F and G is unit, is invertible element. In R. Okay, are there any questions? Okay, if no, let us start the proof of this theorem. Okay, so let us introduce this following set Y, which is a union for I less than J sets where phi of AI here, as usual, I denote by n the number of vertices for a quiver or the number of functions in the seed. by comprimeness assumptions which we made, all these terms are all these functions are coprime, and also this are coprime. So by comprimeness assumption, we have dimension of y is greater than or equal to 2. Now I'm going to use what's sometimes called Hartog's continuation principle. First, Hartog's continuation principle, which says that if some function f, rational function x, is regular outside closed algebraic subset of codimension greater than or equal, then f is regular on the whole variety. Morally, it means that if we have some function, then rational function, then the set of its poles have codimension 1, or it is empty. Probably in such language it is more or less obvious, but this is how to say it. In such language it is more or less obvious, but I should know that we are working not on smooth varieties, but normal varieties. So actually, this probably requires probably some work. But I just use it. The references. The reference can be in some text. So it remains to show that image of your upper cluster algebra is regular on x without y. Okay, so let us show this. Let's take any element, say P, from the upper cluster algebra. Then P is some Laurent polynomial. In terms of P is a Okay. Let me state it in opposite direction. P is Laurent polynomial if in T of A here usual how to say it, better. So let's take any P. Okay, P Laurent polynomial in A1 AN and also A1 AI prime AN, where this is here we use called Laurent phenomenon, which we proved. Now note that since x without y can, so we exclude this in this set, then for any point from x and y, no more than 1 phi of I vanishes, because we excluded the set where two images of two of initial A variables vanish. So if all of this function doesn't vanish, then P is Laurent polynomials on this on the then phi of image of P is Laurent polynomial in with Laurent polynomial with positive coefficients. No, this is not necessary. No, I mean then this Laurent it is positive is not necessary here. It is some Laurent polynomials in phi of P is Laurent polynomials on phi of AI. All phi of AI are regular, doesn't vanish, and only phi of I appear in poles. So for if all phi of phi of AI are non-zero point, then phi of P is also regular. It has no pole. If but it could be that at least one of this function, the point P is 0. Since we excluded this set, then phi of AI prime at point P T is not 0. So we have two properties. This and this. So if one of them is 0, then we have this, and we can write P as a Laurent polynomial on A1, AA prime, AN. Hence, P of PT is not infinity, is well defined. So if all phi of AI on point P are non-zero, then P is Laurent polynomial on then 5P is Laurent polynomial on A1, 5AN, hence 5P is not equal to infinity. If one of them is 0, then we go to the adjacent seed. And that's all. That's proof. Okay, any questions? Now I'm going to apply this theorem to the case of Grassmannians. Let me recall that Grassmannian of Kn is a manifold, points of which are vector subspaces in n-dimensional space of dimension k. I decided to use letters k cap, n capital and k capital signs, and small is my lectures usually related to the number of variables, number of vertices in the C, in the quiver. And in this case, n small will be actually greater than n capital, will be related to it by some formula. Here I defined Grassmannian as a set. If I want to define it as a manifold, one should use some embedding of the set into projective or something. Usually to projective space, this is so-called Plücker embedding. For any vector space V in Ck, we can pick its basis V1, Vk, and we can assign to it the decomposable tensor V1, which V2, and so on, which Vk. And this tensor is defined not uniquely, it depends on the choice of basis, but not very much. If we change the basis, then this volume form will be multiplied by the determinant of the matrix under which we change the basis. So this vector is defined not uniquely, but the one-dimensional vector subspace, the line generated by this vector, is defined uniquely and belongs to the projective space or projectization of the space of K forms on C. This space has dimension n choose K minus 1. So the Plücker embedding is a map from Grassmannian Kn to here. The cluster algebra, in order to have cluster algebra, we need a affine variety. So we take an affine cone of this space. So as I said, this is it consists of all decomposable vectors V1, Vk. And this belongs to. So we take all projective space. So Grassmannian consists of as a certain set of lines, and we take corresponding lines in the KFC. Note this that this affine cone is singular. It is not smooth. Of course, it has, as usual for cones, it has singularity at the origin. Okay, usually Grassmannian also describe, so this Plücker embedding describes in terms of the Plücker coordinates. In order to define them, I again need this basis. So I pick it V1, Vk and write down the, so I fix the basis in Cn. And then I write any vector v, which I had base of v, in terms of this basis e. So say vi is equal to sum xij ej. And I can construct the matrix of this axis. So x11, x12, x1n, and capital. Plücker coordinates delta u1 k are just the minors of this matrix. So determinant of the x I1 x ik1 x maybe not order should be the opposite x1 I1 x1 ik xk I1 xk ik. As I don't know, maybe write different, you take different letter. One gets, I'm not sure that I will just always follow this convention, but one can safely assume that A's are ordered. A1 less than A2 less than AK. Okay, here I plan to say something, but before, another way to define Plücker coordinates is the following. We take the wedge product of, I mean, this is the same way, but just another way to state this. That we take the wedge product V1 Vk, and this sum of delta A1 AK of A1 wedge. So we have Plücker embedding from Grassmannian to projective space, and in projective space we have homogeneous coordinates, and these homogeneous coordinates are exactly the functions, the Plücker coordinate on the Grassmannian. On the Grassmannian itself is a, of course, projective variety, so there is no regular functions on it. So Plücker coordinate on the Grassmannian itself are homogeneous coordinates. They're all defined, their ratios are well defined. They are rational functions, not regular. On the affine cone on the Grassmannian, Plücker coordinate are just regular functions, everything. So we can take, I want to give plenty of remarks. Maybe need more space for them. This is just for future. But up to now, what I want to say is that the functions on the affine are functions on Plücker coordinate. Coordinates modeled by some relations, which I'm not going to write down explicitly. Another way to think of the functions on the another description that ring of the homogeneous functions is has the following formula. So we take this set of such matrices k times n, and there is an action of SLK on this space by multiplication of the left. This action is just the action change of the basis V1 and Vk. as I said, if we change the basis by some matrix from GLK, then such volume form, such wedge product will be multiplied by the determinant of the corresponding matrix. So if we change the basis via SL element of the SLK, then the corresponding wedge product will be fixed. So in particular, only the Blücher coordinates will be fixed. The one can naturally, how to say, we have so for so any function on the affine Grassmannian. Okay, I'm trying to say that this description are in principle two different descriptions. So, for example, any regular function for example, what I'm claiming here that invariant functions are generated by Blücher coordinates. And actually, I proved this for k equal 2, and the proof for general case is the same. It is very important that we actually found some generators, because as I said, when we try to identify some cluster algebra with the algebra given by algebra function, some manifold, some variety, then we have to prove two inclusions, and for one of them we have, as I said, starfish lemma, but for another one we actually we need to find generators. In another way, we have no general theorem. We need to prove it by hand. So we need to find generators and show that they belong to each. So what I'm going to do now, I'm going to prove that this algebra functions affine Konov Grassmannian, the algebra homogeneous function of the Grassmannian is actually has a structure of the cluster algebra, and in particular, I'm going to construct such map phi such that in the image we will have all Blücher coordinates. So the image will generate R. In order to apply starfish lemma, I also need the property that this ring is factorial. I stated the theorem. I'm not going to prove it in detail, with detailed proof, but let me give a sketch. And proof uses this description. So first we take and this is just algebra of polynomials, so this is definitely factorial. And then one have to observe that SLK does not have characters. And hence, the algebra of invariance with respect to this. Hence, we get the statement that algebra of invariance with respect to SLK is also factorial. Okay, let me give it to the new page. Okay, so now our goal is that algebra of homogeneous functions, or algebra of the function and the fungus minor, is isomorphic to the some cluster algebras. We already discussed this for case k equal 2. Maybe I should recall it. This time. Okay. Recall. K equal 2. We have quiver which were assigned to triangulations. So we considered n-gon. See some triangulation. And from this we constructed a quiver. In each triangle we put vertices to the sides of this n-gon and diagonal. We pick the rotation goes clockwise on each triangle. And yes, the names of the variables. So I should label the faces somehow 1, 2, 3, 4, 5, say. And the name of the variables will be just minus here. Will be delta 1, 2, delta 2, 3, delta 3, 4, delta 1, 5. Here is delta 2, 5, and here is delta 2, 4. And in this case, we know that the ring of the we know such as isomorphism. So what I'm going to do today and maybe next time also is analog of this for general K, but maybe in advance I should give some remarks about the structure which we obtain. First, let me remark that we have Looker coordinates, and as I said, they generate this algebra, and actually they will be all of them will be cluster variables. So we will show that belongs to cluster variables. So from this, it will follow that the image of the, not even up, just that the image of the cluster algebra contains R. So in the image of the cluster algebra, we get also generators of R. R is a fine corner of Bershtein. But what is new for this case k greater than 2, that actually it is not equal. So we'll have cluster variables which are not Blücher coordinates. Almost, so I think every time where k is not equal to 2 or k is not equal to n minus 2, which is dual. This is A. B, we'll say that in general, we'll have infinite type cluster algebras. So it means that we will have infinitely many seeds. For k equal 2, all seeds correspond to triangulations. And there are a finite number of triangulations. This is a Catalan number, so okay. We have, it is quite a lot. It grows quadratically with, no, not quadratically. It grows much like, it is like 2n choose n. Grows factorially with the growth of n, but anyway, it is some finite number. But for k is not equal to 2, and except all a few more exceptions, we have infinitely many seeds, so infinitely many variables. So it is not surprised that all of them are Blücher coordinates. We have only finitely many Blücher coordinates. Okay. Remark C said that now cluster monomials are linearly independent. But do not form a basis in for Grassmannian, give it as a problem that they generate R, I think, maybe, but they're always linearly independent. In general, this is not true. And last remark, which is now happily actually the same for R k equal 2 and any k, that construction will depend on the cyclic order of the basic vectors. I usually pick standard cyclic order 1, 2, and so on, and then go through. So it is the order in which I number vertices of this n-gon. And here also everything will depend on cyclic order. So maybe, I mean, this general philosophy that the cluster algebra structure is on some algebra on function, some manifold. It is a structure. It is not unique. So we can take another order and give another cluster structure, another set of variables which are called cluster monomials and so on. Another so cluster varieties glued from toric charts, obtained by gluing from toric charts. So another set of toric charts you obtain if you just change the cyclic order. Okay, any questions?
What is the meaning of word factorial if it is important?
Unique factorization domain. Unique factorization.
Okay.
But maybe not so important. Other questions? Okay, I'm now going to define as I said, the construction Grassmannian, and I'm defining certain seed, which I denote by. So in general, the seed will be denoted by T Kn, but in our case, so this example of T37. Okay, I draw quite a large figure. What you can see here, you see that that the vertices are labeled by rectangles, which belongs to the rectangle K times n minus K. So in this case, the largest rectangle is 3 times 4. And we also include the empty rectangle. So the number of vertices, maybe should. Number of vertices is what? So we should pick one number from 1 to k, one number from k to n minus k, so it will be k times n minus k, but there is also a choice where this one of these numbers is 0, then the rectangle becomes empty, plus 1. So this is exactly dimension of the affine cone. And the way how do I arrange the arrows, I hope is clear. So from this example, so horizontal edges goes to the right, vertical edges goes down, and diagonal edges goes in this direction. There is only one exception, the edge from empty to one box. Two rectangles are connected by vertices which correspond to rectangles are connected by h if the corresponding sizes differs by 1. Anyway, I think everything is clear from the picture. This is secure, but in order to have, but I also have to specify the variables which correspond to each of these vertex. And the formula, again, the examples like this. I didn't draw the arrows on this, so let me add them. Maybe I should say that the arrows, vertices which I put in the box, they're frozen. So in total, how many frozen variables do we have? In this case, 1 plus 1, 2, 3, 4, 5, 6, 7, 8. So in total, we will have n plus 1 frozen vertices. But now I have to explain how did I specify these numbers. And the rule is the following. So for we have a rectangle. Don't know which color to use. Okay, anyway, we have a rectangle, say 3 times 4. So this rectangle k times n minus k. And in this rectangle, we have subrectangle, which correspond to certain vertex. Say this. And hence we have a map. We have a map which goes like this. So this map consists of the, first we go up, then we go right, up, up. Maybe I better to order it in opposite direction. So I will consider this map from the top right corner to the bottom left corner. So this map first goes here to the left, then down, then left, and then down. In general, this map, this path has exactly n minus k arrows going to the left and k arrows which goes to the bottom. And I assign to rectangle a times b, I assign a number of arrows which goes to the bottom. So for example, to rectangle 2 by 2, I assign numbers 3, 4, and 7. And if I take another rectangle, say 1 by 1, then the path will go this way, and the sequence will be as follows. So we first have we first have 3 arrows to the left, then 1 arrow down, then 1 arrow to the left, then 1 arrow down. So in this case, the numbers will be 4, 6, 7. And this is what's actually written here. Okay, so this is how we go from the rectangle to the set of indices. Is it clear?
No, 4 is number of votes and 6.
Number of arrows which goes down. 4, 6, 7.
Sorry, I thought about how many these arrows. Okay, I understand.
The number of, because we go from the right top corner to left bottom corner, then so the number of arrows to the left is always in minus k, arrows to the bottom is always k. But their positions, they are governed by the our rectangle. In principle, I can put here any Young diagram and also get some k element subset of the n. Okay, now is it clear? So I defined okay, so I defined so I defined some seed, and I defined the map. So where we are, we have quiver and a map from the and the map from the say abstract seed with this. Okay, one can say, look, in such way we have seed in R. So seed consists of the quiver Q and minus di dA, which were defined above. So in the any questions? So now dA belongs to R. The sum of the Blücher coordinates. As I said, it is not true that all cluster variables will be Blücher coordinates, but there are quite a few seeds in which all variables are Blücher coordinates, and I just start from one of them and define everything via it. Okay, there are a lot of seeds where all variables are cluster coordinates. I will say a bit more about this next time. So there is some combinatorial tool which replaced triangulations, which we had for k equals 2. But before this, let me just give one problem, which is straightforward, but maybe I will use it today in the proof, which says the following. So we can take this seed, tkn, and mutate each row from the left to the right, starting going from bottom to the top. So here, 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 and then here, here, here. The problem states the following: that after this transformation, actually we'll have up to the same seed as above. So the quiver which we obtain will be isomorphic to the initial quiver. And so if we get the same quiver, but each set A will change to A plus 1. It means that we have, so here we had some set A1, AK, change it A1 plus 1, AK plus 1, modulo mod. In particular, one can see what's going on the frozen part. This set of indexes which we have here, they consist of k consecutive integers. 3, 4, 5, 2, 3, 4, 1, 2, 3. This is also actually 7, 1, 2, because we have a cyclic order. This is also a set of 3 consecutive integers. So if we just add them by 1, it will mean that we make some rotation by 2 pi over n, by the angle 2 pi over n. And so this sequence of mutations is actually equivalent to such rotation. Example, one more example is that if we take triangulation, so here we actually pick some triangulation such that all diagonals go from one vertex. If we perform 2 mutations, sorry, maybe for pentagon this is not very clever. Let me take what can I take? 7. Okay, all diagonals goes from one vertex. Okay, now we do this sequence of mutations. Let me do it. Here I had some description, so we should go for order rows from bottom to the top, from left to the right. In this case, as we have only one row, and from left to the right means some order on this diagonal. Say maybe this or opposite, doesn't matter. Let me pick from left to the right. So first I do this mutation. Then I do this mutation. Then I do this mutation. And then I do this mutation. So you see, we have a rotation of the figure. Before we have, say, all diagonals goes from 1, and now all diagonals goes to -1, which is 7. So maybe here is not 1, but -1. It is, so here -1, but it is not very good. Okay, this is one more example, and actually I will use this property in the proof. How much time do I have? Okay. Maybe before proving, I want to show you some more figures. Okay, I want to show you this. Okay, do you see my screen now?
Yes.
Okay,
Yes.
this is an app. This is so-called queer mutation app, which is developed by Bernard Kellier. It is a very famous app. Everybody uses it. And it has many tools. For example, it has the Grassmannian tools. So you activate Grassmannian. I have to enter KNN. Let me enter, for example, 4, 9. Okay. There are two grids, square and triangle. I actually use here triangle grid. That is, you see picture consists of triangles. So this is what I wrote, just rotated. And there are a lot of interesting stuff here. For example, here you can see what corresponds to Plucker coordinates. Plucker coordinates here. I'm not 100% sure that convention is the same as in my talk, but up to some details. So maybe here it is the opposite, or convention is opposite, but not very important. And and here you can also see the colors of the vertices. So blue vertices, I hope you see the colors, are frozen. We cannot mutate in them. And now we have green and yellow. I'm not sure that I know all details. I didn't find documentation. But what is important about green? They have valency 4. We'll have and therefore valency 4 vertices are very good for mutations. We have 3-term relations, like xy is equal to b plus ct. And if we mutate in vertex of yellow vertex, then there's not 3-term relations, there's no Plucker relations. So after mutation, we get not Plucker code. But okay, now let me perform what I asked you. So if I just plug on push on, so if I just do see my mouse.
Yes.
Here I do mutations. So here, 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 here. Okay, and maybe it is difficult to see anything from this picture, but you should know that you should ignore all ages between frozen variables. And after this, you can see here again triangle grid, but it is somehow rotated. Maybe I will not try to just rearrange it to the figure which we had before, but okay. Okay, this is I wanted to show you as some sort of entertainment. Okay, now before proving, I need a couple of tools. First, remark that there is an isomorphism between functions on Grassmannian Kn and function on the dual Grassmannian. which sends any minor to dual minor. And this is actually isomorphism between corresponding seed patterns. Another remark. Or maybe I put it not as a remark, but as a lemma. Exist embedding of the functional Grassmannian k minus 1 n minus 1 into function of the Grassmannian kn, which sends any minor here, delta a, to minor delta a n. So the map is defined. Actually, one have to show that all Plücker relations are satisfied under such map. It is more or less straightforward. Now maybe how much time do I have? I have 10 minutes. This A, B. This agrees with cluster structures. In what sense? In the sense that here you can actually find, so this is the figure for Grassmannian 3,7, but if you delete this row and then erase this number 7 everywhere, then you actually find the seed for the Grassmannian of k minus 1 n minus 1. Okay, this is one. And now let me state corollary. Any Plücker coordinate delta I is cluster variable. Before proving this corollary, I want to make corollary from corollary. It says that R is, which is homogeneous function of the Grassmannian, is embedded to the cluster algebra, because R is generated by Plücker coordinates, so we have an embedding. We don't know that this exclusion because we don't. There are much more. At principle, there are more cluster variables in A. So A can be larger. A can contain some functions which are rational. This is not the case, but we will prove it using Starfish. Okay, now the proof of the corollary. Since I have just a few minutes, I will be sketchy, but the arguments go. The logic is as follows. First, it is sufficient to consider case where the set A is some set A prime and n. So it is sufficient to consider a case where I have problem. Sorry, yes, maybe not I. Maybe I'll change it through the whole lecture. So this set of indices I, maybe I just now realized that my letter A is overused. Never mind. So we have this sufficient to consider a case where the set of indices includes the largest one, n. Why? Because if it doesn't include, we can apply this problem, which shifts all indices by 1. And shifting all indices by 1, we can send any set of indices to set which includes n. And in this case, we can use the lemma. And induction, which will set that delta I prime is cluster variable, but for the previous Grassmannian k minus 1 n. Okay, this is a proof. Not working. Okay, and now the main theorem is the following: that ring of homogeneous function of the Grassmannian is isomorphic to a cluster algebra. Proof. For the proof, we need to show that we already have one embedding. We need to show the opposite embedding. So we plan to use starfish lemma. In order to, in starfish lemma, we have some natural assumptions on this Grassmannian, since this is normal, and, it is reducible, and so on, which are satisfied. Normality follows from factoriality and so on. And we have to check some properties of the coprimeness. And for coprimeness, we know that any delta I is determinant. Hence, it is a reducible polynomial in X. Hence, delta I and delta I prime are coprime for I not equal to I prime. This is not the end of the proof. It remains to check, maybe not a prime, J, to check coprimeness. So this is so from here we prove that, for example, we prove that all initial cluster variables, which are all Kluger coordinates, are coprime, pairwise coprime. But we also have to check that any cluster variable is coprime to what we get after mutations. So it remains to check the coprimeness of any delta I, okay, of any AI and A prime I. AI is a sum minor if, and here we have two cases. If A prime is dealt on some E prime, then we're done. And secretly, this is equivalent to the fact that the vertex I is 4-valent vertex. And second case, if AI prime is equal and actually equal to something. Delta delta minus delta delta. Then we have to check. And I omit this equation. Anyway, so we have to check we have to do mutation in any vertex and check that the resulting variable is coprime to this. It will be much easier if we start from the seat where not only just all the initial vertices are initial variables are Kluger coordinates, but all vertices which are obtained after mutation also Kluger coordinates. Actually, such sheet exists, and we will discuss. But I don't know. Okay, so this is the end of the proof of the theorem that on there is a cluster structure on the Grassmann. Here I gave this structure just ad hoc without any motivation, how it is related to something which we saw before or anything like this. I will try to make some more motivations and connections next time. Okay, that's all for today. Questions?
But can we write explicitly maps from Grassmannian to cluster variety and vice versa?
I think we wrote it. The map was from, I don't know, in terms of algebra, the map was from cluster algebra to the algebra function of the Grassmannian. We have A variables which correspond to this, quiver, go to corresponding minors, corresponding Kluger coordinates. Okay.
And in the how to obtain map in different
for generic in terms of the point. I mean, this okay. This cluster, these minors, they generate the algebra of rational functions. So if you want, you know what are the preimages of these minors, and therefore you know the preimage of any rational function. maybe I should say that I think that here there's no difference between general k and k equal 2. So if you, so we should, any problem of such kind should be first considered for k equal 2, or at least something is simpler. Okay, yes.
Okay.
Other questions?